So the next talk is by Hugo from Census Labs, and it's about racing against the Android kernel. Let's see who wins the race.
Hello, everyone. First and foremost, thank you very much for being here. I do not take it for granted that you are here to attend my presentation, so thank you very much. So we will be discussing 4 novel techniques for forcing the Android kernel to block, that is, delay execution, thus allowing attackers to win race conditions more easily. As opposed to many other exploitation-related presentations, we won't be looking at specific vulnerabilities, but we will be discussing about techniques that you guys can use in your own exploits. But let me first introduce myself. My name is Chariton Karamitas, or Huku. I'm a vulnerability researcher at Census, specializing on Android since 2015. I'm a binary diffing PhD student, and also a proud, many times, FRAC author. So without further ado, let's discuss about race conditions. So race conditions can take many forms. Sometimes this form might be a parallel access to a global resource. And in this case, attackers usually race against the lock and unlock primitives on this global resource, or the lack of these primitives. Other times, race conditions concern the lifetime of a memory allocation. So attackers race against the allocation and the allocation of a certain memory region. And most often, race conditions take the form of classic time of check, time of use vulnerabilities. Let me give you some specific examples. In racing against the clock, Jan Horn, I don't know if I'm pronouncing the name correctly, uses userfoldfd to win one of the 2 races that he's discussing in his article. In Linux kernel universal heap spray, Vital Nikolenko uses userfoldfd, a known technique used for blocking the kernel, in order to extend the lifetime of heap allocation, thus achieving a more reliable and stable heap spray. And last but not least, a classic time of check, time of use vulnerability, not vulnerability, a technique actually that I really like is the dirty cred, which is about a check performed on the cred structures on the kernel corresponding to certain sensitive objects like file objects and so on. So what is common in all those examples? All of these examples basically force the kernel to delay execution when accessing a certain piece of memory. And to do this, attackers usually use a system called userfoldfd. So this used to be a great tool at the hands of exploiters up until not recently, actually, it's been quite long, since CCTL knob was introduced, prohibiting unprivileged processes from using that system call. Now, on Android, in the past, this wasn't even available because it wasn't used anywhere, and vendors proactively disabled it in the kernel configuration in order to prohibit attackers from making use of these techniques. Now, recently, on Android 13, userfoldfd was introduced in the kernel configuration because the new garbage collector in the ART runtime makes use of it. But we all know that Android internals change a lot, they change often, and they change dramatically. So we know that userfoldfd is supported on Android 13, but will it be there on Android 16 or 17? Now, an alternative technique to userfoldfd is the one using the userland file systems, or Fuse. So on desktops, Fuse is a very powerful alternative to userfoldfd because dev Fuse has satanic permissions. And also, user mount is a suid root binary. So unprivileged applications can actually use it. Now, on Android, this isn't the case. Dev Fuse is owned by root. There are no suid binaries. There's also AC Linux, which basically prohibits all applications from accessing this device, apart from a very limited set of privileged daemons. So there's a common misconception that on Android, Fuse cannot be used for exploitation purposes. Now, we need a set of techniques for achieving the same principles like those that userfoldfd achieves. Ideally, techniques that are hard to mitigate because they're based on architectural design choices. So here we'll have a look at 4 of them. 3 of these are actually based on Fuse and can be used from the untrusted SE Linux context. And another one is based on the incremental file system, a relatively new file system introduced on Android, and can be executed from the system app and system server SE Linux domains. But before we begin, so why Fuse is how come Fuse is used on Android? What's the use case? So Fuse is used by 2 major mechanisms on the framework on Android. One is the scope storage, and the other are the proxy file descriptors. We will talk about them later. But basically, what happens is that those 2 mechanisms basically allow an attacker to make use of devFuse to achieve the exploitation primitives that they like at the cost of additional complications. But before we begin with the actual techniques, let's discuss some previous work on race conditions. To win race conditions, attackers usually use several tricks. The most common ones are scheduling tricks, like changing the CPU affinity or the priority of a thread. More recently, attackers started using forced preemption based on inter-processor interrupts, high-resolution timers, also hardware IQs coming from external devices. There's another technique referred to as the resource monopolization. Basically, what happens here is that a thread that has access to a global resource, like a PCI bus, for example, monopolizes that bus, thus prohibiting other threads to be scheduled in. And this gives time to the attackers to exploit certain race conditions. But I haven't seen it being used in practice, to be honest. Another case of techniques is the so-called performance degradation techniques. That is the introduction of delays in threads, which allow an attacker to, let's say, to a certain extent, mess with the scheduling order of threads. And to do this, we can use several techniques. So the most common ones are caching and page fault techniques. So in this case, attackers can make a certain cache line or a certain set of cache lines, either hot or cold, depending on the result they want to achieve. Or they can use reads from slow file systems, like network file systems, or multiple layers of device mapper file systems. And of course, the userfoldfd and the custom fuse daemon techniques basically fall under this category. Now, one might say that those last 2 could also have been categorized under the blocking I/O, which also contains techniques like reading from empty FIFOs, like pipes, which is a very common exploitation technique for Android kernels, or even writing to full pipes, which is actually the opposite. And last but not least, when dealing with races that act on file objects, usually file locks are used, either explicit or implicit, either mandatory or advisory. The exploitation techniques that we'll be discussing fall under these categories. The proxy file descriptors and the IncFS are kind of similar to the userfoldfd and the custom fuse daemon techniques, while reduction and transcoding, the other 2 techniques that we will have a look at, are blocking I/O techniques. So let's start with proxy file descriptors. First and foremost, proxy file descriptors are an abstraction over Fuse. The end result is that any file-related system call performed on the proxy file descriptor is actually translated to an asynchronous callback in a Java code. So you have a Java class that implements some callbacks, like on read, on write, on this, on the other. And when a certain system call is executed on the proxy file descriptor, the corresponding callback is executed. Let's see a very simple high-level example. We have 2 applications, one on the left, one on the right. Let's say the application on the left is the producer, and the application on the right is the consumer. The producer communicates with system server and receives a proxy file descriptor. The producer also implements the aforementioned system calls. Now, this file descriptor can be passed over to another application, the consumer. When the consumer performs a read operation on this file descriptor, the producer is notified by the kernel, and let's say it communicates with the network to receive some network resource, some file, and when the response comes, the data is sent back to the consumer. Now, that was an example, right? But what is the actual use case of proxy file descriptors in the Android framework? Well, the actual use case are the revocable file descriptors. What happens here is that, let's say system server needs to open a sensitive file that has some sensitive data in it, but it wants to explicitly control the lifetime of this file. Now, if system server sent that file to another application, that would increase the reference count of the file object. So if the system server closes the file still remains open until both ends actually close it. Now, what happens is that system server creates a proxy file descriptor, sends over the proxy file descriptor to another application, and all callbacks of the proxy file descriptor act as a bridge, let's say, to the sensitive file descriptor. So at any point in time, system server can close the sensitive file descriptor, and in this case, the remote end cannot read anything or write to it, whatever. This is how it is implemented. We have a simple class named the revocable file descriptor. You can see a miner, which is the sensitive part, a mouter, the proxy file descriptor, and a boolean named revoked, which indicates whether access to the sensitive file has been revoked or not. The constructor just initializes a miner to whatever FD file descriptor the system server wants, and a mouter is set to a new proxy file descriptor. System server at any time can call revoke to set the boolean to true. And next, the onRead implementation, as you can see here, of the proxy file descriptor, calls checks revoked, and then proceeds by reading from the actual sensitive file descriptor. Any data that is read is forwarded back to the client. Now, at any time, system server can set the revoked flag to true, and then any attempt to read from the underlying file descriptor will result in an exception. And this is how this actually happens at the background. An application wishes to create a proxy file descriptor, so it communicates with system server. To do that, it needs to implement the set of callbacks that we have discussed. These are called the proxy file descriptor callbacks. In this case, let's say that we have only one, on read. So we implement it, and we insert a delay, thread sleep for 2 seconds. What the application does next, it communicates with a storage manager service and calls open proxy file descriptor. Now, system server running under the system UID 1000 cannot open dev fuse because it's only readable by root. So what it does is that it communicates with volD. It calls mount up fuse, method exposed by volD. And this is only performed the very first time an application wishes to open a proxy file descriptor. Now, volD communicates with the kernel and so on, and mounts fuse file system under a directory named mnt_app_fused and an identifier consisting of information of the original caller, the application. Now, this step completes the preparation of the fuse mount bridge, as it is termed in the Android internals. And what happens next is that the dev fuse FD that was used to create the fuse mount point is sent back to the system server. Now, the system server does not trust the application. So instead of sending over the fuse FD to the application, it creates a socket pair, sends one end to the application, and the other end acts as a bridge between the one end of the socket pair and the dev fuse file descriptor. And in there, a simple stub is implemented for translating commands back and forth. Next step, so after the Fuse bridge has been created, during the same call to open proxy file descriptor, system server calls open up Fuse file, another method which is exposed by vol_d. In this case, vol_d creates a file under the aforementioned mount point. The file is named after a simple incremental identifier. It doesn't matter because, in any case, Fuse files are not referred to by their name, but by the file descriptor. So the file is opened, and the file descriptor now is returned as is to the application. Of course, the application can map this file descriptor in memory, like normally any other file descriptor. And of course, it can pass it to a system call to the kernel. Now, when the kernel attempts to read from that memory region, a page fault will occur. The corresponding on-read callback will be executed, and the execution will be delayed. Success. As an added bonus, of course, a proxy file descriptor is a file descriptor, so we can send it to any other application in any other form of a race condition, let's say, and we can make any other application block, or even we can block ourselves, right? If we make use of the file descriptor, we block ourselves. So this is the overall architecture of the proxy file descriptor subsystem. It's quite complicated. I tried to replicate it here. And it's mostly meant for people that will download the slides later so that they can read it themselves. So I think we have enough information to create a proof of concept, right? So what we do is that we implement our own on-read and on-write callbacks. We use open proxy file descriptor. We map the file descriptor and pass it to any system call that will access this memory region. And we will see how it faults and blocks. I hope you can guys see that. So in this case, I have created a sample application that basically performs all the aforementioned steps. I just click Start. The application seems to be stuck for a while. OK, so I randomly picked a uname as a system call. And we can see here that, I don't know if you can see that, calling uname. And after 2 seconds, because I've set the sleep time to 2 seconds, the process returns. So I don't have enough time to show the code in detail, so feel free to catch up with me later. I'll be around here. If you want to see the code, I will show it to you. And now let's move on to the next two techniques, reduction and transcoding. So as we mentioned previously, Fuse is used by scope storage. Scope storage is actually the modern way of accessing files under SD card on Android. It's the successor to SD card FS, and is basically implemented in a process called the media provider. The media provider, of course, is a very interesting attack surface by itself. The benefits it offers compared to its predecessors are improved developer experience, fine-grained access control, and increased privacy. And the two I have highlighted are actually the features that our techniques are based on. Let's see how this works. We have the media provider process. And the media provider process implements a Fuse daemon. The Fuse daemon is written in C++, and that's why it's very interesting, to be honest. So the Fuse daemon creates a mount point under the SD card directory. So any application that attempts to open files under that directory will result in the kernel notifying the Fuse daemon handling the request. The Fuse daemon, of course, using J and I, can call internal Java methods in the media provider process. Lots of stuff happen there. And then a response is eventually returned back to the user, to the application. Now, there are two features of the media provider process which are not very famous. One is the reduction capability, and the other is the transcoding capability. Reduction means that media provider can optionally filter out sensitive data from media files, like EXIF tags, holding location information, and the corresponding ISO boxes in media formats that are composed of ISO boxes, like MP4, for example. Transcoding is the process of converting one media format to another. The reason this happens is because some applications may not support certain media files, so the media provider automatically converts so that any application can access, for example, a specific video on the device. And this is how it works. Let's say we have a camera application. You open the camera application and you capture a video. That video might be written in high-definition format, HDR or HEVC, I don't know that. But let's say that you also have a media player application on your device, and that media application is a legacy application and does not support these high-definition modern formats. So it can request that the media provider transcodes those high-definition videos to lower-definition videos. And at the same time, it can request that any sensitive information in the media files are replaced by zeros. And the media provider can do that transparently while the actual content of the media file is being streamed to the original caller. The implementation, of course, is based on Fuse. So the media provider starts up and uses libfuse to create the mount point under storage emulated 0, or SD card for short, and passes a struct to that function. That struct holds the callbacks that will be executed when certain system calls are performed on files under the SD card mount point. Now, let's say we have an application that opens a file under SD card. Let's say SD card pictures, picture.jpg. This can happen either by using system calls directly, like open, or using indirect methods of accessing files, like a third-party content provider. Now, the kernel knows that this mount point is being handled by the media provider, so it notifies the corresponding process. The media provider, of course, can perform arbitrary actions before replying to the user, and eventually the user, when the open system call returns, receives a file descriptor, which is actually a Fuse file descriptor, and can be mapped as we saw previously. So, briefly, calling open at the application side results in calling pfopen in media provider. Doing read at the application side results in calling pfread on the media provider. So if we map that file descriptor and pass it to the kernel, during the page fault, pfread will be called to populate the page cache. So theoretically, if we manage to force the media provider to perform extra work during pfread, then we will achieve the same result as user fault fd, for example. But let's see what happens when pfopen is called. After doing some trivial parsing of open flags and so on, pfopen calls into Java, and more specifically, a method called onFileOpen, which is this one. What this does is that it checks that the path being opened is a redacted path, a synthetic path, and a redacted path at the same time. Then it notifies the transcoding helper in case transcoding was requested, and also fetches the reduction ranges in case reduction was also requested. Let's start with the reduction ranges. What are the reduction ranges? So if you have a media file, a list you have also a list of sensitive EXIF tags holding location information. All those tags are looked up in the media file being processed, and their offset and size are also appended in an array. The same, of course, happens for media files based on ISO boxes, like MP4 media. We have a list of sensitive ISO boxes the offset of those ISO boxes are looked up in the media file, and their offsets and sizes are placed in an array. So the concatenation of these two is actually the list of redacted ranges, or to-be redacted ranges in the media file. And this is the list of sensitive EXIF tags and ISO boxes. As you can see, all of them are related to GPS coordinates. I have highlighted one here, which is the one that our proof of concept will use later on. And I will explain why I decided to use an MP4 box instead of an EXIF tag. So the way the parser works for EXIF tags is as follows. The very first time a specific tag is located in the media file, it is used for reduction purposes. So any other similarly named EXIF tags are ignored, basically. On the other hand, media files which are based on ISO boxes have a tree-like format, a tree-like structure. So what happens is that the media provider will flatten that tree, will create a huge array of all ISO boxes in the media file, and will try to find all ISO boxes in the media file that have a type which should be redacted. So we can have several, we cannot have several GPS location EXIF tags, but we can have several ISO boxes that also hold location information. Let's keep this in mind. And now let's get back to the synthetic directories and the redacted directories. What are those? So if we look at the code, we will see that a synthetic directory looks like that. Replace the first three elements with /sdcard, and you get sdcard.transforms/synthetic. OK. And how does a redacted path look like? Well, it looks very similar. It's basically the same with redacted appended, and the file names have a pattern that consists of the constant RUID followed by 32 random characters. Now, these files look quite suspicious, right? So applications are not supposed to create these files under the SD card. Indeed, the media provider does. So the media provider has a method which is called getRedactedURI. As you can see in the third highlight, the file name of the redacted file is created. The first constant holds the RUID prefix, and the remaining 32-bit characters basically come from a random UUID. And how do we call that? Well, media provider is actually a content provider. And content providers optionally can implement a method called call, which allows for implementing arbitrary APIs. And the media provider provides an API for calling getRedactedURI directly. And instead of doing it directly, there is another class, which is called the media store. And the media store is a front end to the media provider. So it will save us from some trouble. The media store will perform all the steps automatically. We just need to pass one or two arguments. OK, so far so good. So now we know that when an application opens a file under the SD card, the media provider is notified. It will fetch the list of redacted ranges, and it will inform the transcoding helper. But we said that in order to block the kernel, we need to insert delays during the PF read. So let's see what happens when we do PF read, when we actually read from the opened file. So PF read will first call transform. It's the method that performs all the transcoding process. And if reduction was requested, it will call do read with reduction. Let's start with the latter first. Do read with reduction is pretty straightforward. It basically iterates through the aforementioned sensitive ranges in the file. And for each such range, it will replace the data in the corresponding offset and size with zeros. So if we have a media file with, let's say, hundreds of thousands of sensitive ISO boxes, this loop will take quite some time to be processed. And this will eventually introduce delays. And so now we have enough information for our first proof of concept. What we do is that we create a simple test.mp4 file. We append 500,000 sensitive ISO boxes in that file. We use getReducted URI to fetch a reducted URI to that file. And when we open it, we receive a file descriptor, which is actually a fuse file. We map it. And when the kernel accesses the memory region, it results in the media server being notified, and the media server begins the reduction process, which takes time. And this will eventually stall kernel execution. Let's see it in practice. So let's say the first argument is the number of boxes that I need to insert. Let's say 500,000. I kill the media, provide the process every time to start from a pristine state. So if it fails, it's OK. I think it hasn't failed. Great. Now, I have fetched a reducted URI, as you can see. I map it at this address. And then I execute a system call that accesses that memory region. It doesn't matter which one. And we measure the time it takes for the system call to return. And we see here that it takes 316 milliseconds. Now, if you don't believe me that this is because of the number of ISO boxes, I can set this to 1,000. Same thing happens. We wait for a while for the media provider to start. OK, so YouTube failed to start. Let's do it again. So what I do here, I forgot to mention, is that instead of developing my own application, what I do is that I attach to YouTube, and I use Frida to execute the proof of concept within the YouTube process. And as you can see here, with 1,000 ISO boxes, we get an access time of 2 milliseconds. Compare that to the previous one, which was like 300 something. So now let's continue with transcoding. Transcoding is completely different from reduction. Of course, it can take place at the same time, but you can use one or the other or both. Transcoding uses a countdown latch and queues a transcoding session, and then waits for that session to return. Now, a transcoding session is nothing really complex. So basically, the media server communicates with a service called the Media Transcoding Manager that communicates with the media processing subsystem on Android, and which also does the transcoding. And then calls an API exposed by that service to enqueue that request to the processing queue of the service. And then it uses the aforementioned countdown latch to wait for this processing to finish. Now, the interesting part here is that media provider cannot know in advance how much it will take for the transcoding to finish. So it has a simple heuristic, get transcode timeout in seconds, that computes a theoretical timeout based on the file size. And so the aforementioned latch is used to wait that amount of time. So to use transcoding, this property needs to be enabled. In most devices that I've seen, in most modern devices, because transcoding was introduced, I think, on Android 11, I'm not sure, or 12. On most devices that I've seen, this one is enabled to true by default. Now, once this is, even though this is enabled, this doesn't mean that transcoding will be used automatically. So for transcoding to be enabled, the source application doing the media access needs to use either specific APIs to force the transcoding, or it needs to have certain attributes in its manifest to indicate that certain high-definition video formats are not supported. But for demonstration purposes, and because I'm using YouTube for this proof of concept, I hook the media provider to force transcoding. So let's also have a look at the transcoding proof of concept. It's basically quite similar to the previous one. So I have downloaded a high-definition video that I found in a site that has media samples. In this case, we hook the media provider to believe that YouTube needs transcoding. And then we open the file, we request transcoding, we map the file descriptor that we receive from the media provider, and then we pass it to the kernel. We measure the time it takes for the system call to return, and it takes almost 1 second and a few milliseconds. So far, we had a look at 3 techniques that can be used from the untrusted app SE Linux domain. Now, we'll have a look at another technique which can be used from system app and system server. This technique is based on the incremental file system. So what is the incremental file system? It's a custom file system which is only found on Android and basically enables developers to stream applications from ADB to the device. What this means is that, let's say you have a very large APK. You can arrange the APK in such a way that some important stuff, let's say, is present at the very beginning of the APK. And then you stream the APK to the device, and the application can start running before installation finishes. Now, this was meant especially for game developers, because game APKs have a huge number of resources and images and so on. And it makes it easier for them to test on their development devices. However, incremental FS is much powerful than that, and theoretically, it can be used for streaming applications directly from Google Play. If it's not being used for that purpose already, I don't know. So IncFS, incremental FS, or IncFS for short, is a stackable file system. So when you mount it, you need to mount it over an existing file system. So in this example, I have a rooted device, and I do mount -t incremental FS. I mount the backing store to a directory named mount. The names that I have chosen here are not very random. The source directory is usually called the backing store, and the target is called the mount. So when you do that, some special files automatically appear under the mount directory. As you can see here, there's an entry called pending reads. In order to interact with this file system, you need to open this file and perform IOCTL on this file. There are basically two important IOCTL codes, one for creating a file and another for populating the file with data blocks. And this is how it works. We have a data producer. The data producer mounts backing store on mount. This can either happen by communicating directly with the Vault daemon using mount incfs and unmount incfs, respectively. Or in case of an application or a system application running under the system app SE Linux context, this can happen indirectly via the incremental service, but we won't have a look at this one here. Now, let's say we have the data producer creates a file under the file system. Let's say test.txt. Once the IOCTL completes, the file magically appears in both ends, both in the mount directory as well as the backing store. Now, a data consumer that needs to read the data in test.txt opens the file and calls read. Now, at this point, the consumer will block, because this is how IncFS works, and because there is no data in the file. The producer can at any time unblock the reader by writing a block of data in the file. This can happen with the corresponding IOCTL code that I showed previously. But the thing is that the consumer can open that file, map it, and pass it to the kernel. for a system call, for example. Now, the same process of blocking will also be followed when the kernel page faults while reading from that memory region. To understand why this happens, let's have a look at how the IncFS driver is implemented. So for the initiated, the file operations for the IncFS is set to generic file read iter, which is a generic function in the kernel, so that the IncFS driver does not have to deal with IOVEX and so on. To actually populate the file, the driver uses the read folio function pointer in the address operations, which is responsible for directly populating the page cache. So what happens is that the corresponding offset is, where the consumer awaits for data is translated to a block index. So files are split in blocks in the IncFS model for performance purposes. And the block index is passed to read single page timeouts, whatever. And this method computes a timeout to wait for the data to arrive. Now, this is normally configurable using mount options. But on Android, the Vol daemon hard codes that to 4 seconds, if I'm not mistaken. And wait for data block eventually creates a pending read, let's say, and inserts it in a queue. And after inserting it, it calls wait event interruptible, which actually spin locks until a certain condition is met. And once the corresponding the data corresponding to this pending read has arrived, the loop breaks and the pending read is removed from the queue. Now, this is the read side of the driver. The write side of the driver also depends on an IOCTL, as we have discussed. So basically, an IOCTL is issued, certain data is written in the file, actually a block is created, and the block is added in the file at the corresponding offset. And then notify pending reads is called, which iterates this list of pending reads that we saw previously, and it wakes up all tasks that have blocked waiting for the read to complete. And now, we also have enough information to construct a proof of concept for this technique as well. So what we do is that we get the iVol-D binder interface if we're running under the system server SC Linux context. Or if we're a system app, we do this indirectly using the incremental service. But we won't have a look at it. We create the banking story mount directories, and we use the corresponding callbacks in Vol-D to create the mount point. We create an empty file, test.txt. And in the same process, we open and map that file and pass it to the kernel. Now, before doing that, we create a thread. And that thread waits for some time and then issues another IOCTL to populate test.txt with some data. When this happens, the kernel unblocks and execution is resumed. So let's have a look at this final proof of concept. Now, instead of doing it from system server, I have created a standalone binary called IncFS proof of concept. We execute it. So the main thread passes the mapped IncFS file to the kernel. This output here does not matter, ignore it. But what happens next is that we have already created another thread. It waits 1 second, and then populates the file, and then the kernel returns. So the system call takes about 3 seconds. And this completes the proof of concepts for today. A few conclusions and takeaways. So we have showcased 4 novel techniques for forcing the Android kernel to block in a fashion similar to user-fault-fd. These techniques are available to untrusted app, system app, and system server SC Linux context. And these contexts are not random. They're actually the contexts from where attackers usually execute further attacks like KernelLPs. For a long time, Fuse was considered unusable. Maybe no one ever wanted to talk about it. I don't know. So if you dig in deep enough in the OSP ecosystem, you will find hidden gems. There are many, many more, believe me. And maybe we will talk about them next year. Thank you very much. And I think we have enough time for questions, right? No.
Sorry, just a very basic question. What's the use for breaking out of a system app and doing this delay from there?
Sorry?
What's the use for using this delay in the system app? And untrusted app, I understand.
OK, so the delay, so basically a system app can delay the kernel. Yeah. And that is important because in many exploit chains, you elevate from an untrusted app to a buggy system app. And then from the system app, you execute an LPE. And blocking might be useful for the LPE.
Thank you for the talk. It was really insightful.
Thank you.
My question is about the first two methods. So comparing the fuse mount and open Proxy5 descriptor with the second method of transcribing and reduction, does the second method with the transcribing and reduction provide any advantages? Because I think with user fault FD, you can not use it with fuse. You can have like really precise control over the memory access operation, whereas the other seems
so
more
in fact, the transcoding and reduction techniques are inferior to the proxy file descriptor. But I'm afraid that at some point something will change and the proxy file descriptors will not be usable. So you will have alternatives.
Fingers crossed. Thank you.
Thank you.
Right. Any more questions? Thank you so much for the talk, Dan.
Thank you.